All right, I think we're recording now. All right, so today we're going to continue studying three-dimensional space, and one common thing, one common mathematical object we're going to be using in three-dimensional space is called a vector. Now, for people in the chat and both people here, have you guys heard or seen vectors before? Is the who in the live audience, who's seen a vector? Who's heard that word? Okay, that's almost everybody. Okay, so thankfully this probably won't be new for too many people. Yeah, in the chat I'm seeing physics. Yeah, there's definitely a lot of vectors in physics. It's one of the most basic objects there too. So, all right, that's a good sign. All right, well let's remind ourselves what a vector is. A vector is an object with magnitude or size and direction or orientation. So far in calculus, we've kind of restricted our attention to what are called scalars, or just ordinary numbers like 2 or pi or 10 or whatever. Vectors are a bit more complicated because not only do they have a size, like 3 is bigger than 2, but they also have a particular direction that they're pointing in. And as we're going to see a lot later, especially, vectors are an important tool for us to understand calculus in 3 or more dimensions. So that's why we're going to kind of learn about the basics of them here. All right, let's see. So a vector represented by the directed line segment AB has initial point A and terminal point B, and its length is denoted with this. So whenever you see an absolute value sign, whenever you see an absolute value sign, that's indicating how long your given vector is here. All right, so we're going to kind of start thinking of them as something pointing from A to B, but really they're much more general than that as well. Two vectors are equal if they have the same length and direction. Now notice something that wasn't here, not position. So for example, if I drew this vector like this, so this has this length and is pointing this way, and I drew another vector over here, even though they're not in the same place, these are exactly the same vector. These vectors are equal because they have the same length and they're pointing the same way. And they do not need to be in the same place. So that's our first kind of interesting fact about vectors. All right, let's see here. Graphically, vectors can be added, subtracted, and multiplied by a scalar. So to kind of illustrate this, we're going to have these two example vectors here. And for those of you who know about them, you know that vectors often have like components, like your x component, your y component. We're just going to look at them graphically for now, and then we'll get to the components or algebraic part later. So we have u, it's a little small vector pointing northeast, it looks like. And then we have v, which is a bit longer, and it's pointing to the right here. Now, what happens if we add two vectors together? What does that actually mean? Well, there's kind of two ways to interpret this. There's the vector addition where we can start from the beginning of the first vector and go to the end of the second one. So if I were to start from here, my vector would end up going all the way over here. And this would be the vector u plus v. And this method of addition, this often has the name tip to tail. I think that's a pretty common name for it. But essentially, you start from the beginning of the first vector and go to the end of the second vector here. All right, now another way of adding vectors is called the parallelogram method.
Targeted laptop. We go to
Always
this
paranoid I'm going to spell this wrong.
Going
I think I spelled it correctly.
This is
Mute,
anyway,
please.
parallelogram.
productivity.
So what we do is we have both of the vectors joined at the same
Can you
time,
please mute?
and we sort of make
As
two
you're
copies
eating.
of them. One
Also,
at the end of the first vector here, and then
What's cool about this?
No,
vector.
mute your mic.
And wherever they
Hey,
meet, wherever these
no!
lines cross like this, there's going to be a vector going diagonally. All right, for those of you online, make sure you mute yourselves when you come in. Oh, it looks like everyone's muted here. Let me make sure. Okay. All right, there we go. If I please repeat everything. Yeah, all right, let me go back a second. I think there was some issue with the audio. Did you guys hear the tip to tail part? Was that okay? Okay, that was okay. All right, so the parallelogram method is another way of adding vectors. We effectively make a copy of this one at the end of the other vector, and then we do the same thing up here. So notice this is a copy of V, and this is a copy of U. And wherever they meet, we draw this line right here, the sort of diagonal through the parallelogram, and that's going to be our U plus V. We have a question in the chat, is it the same vector as over here? Yes, they're absolutely the same. And if you kind of look at the pictures here, this is the same vector as this. It's just in a different location here. Remember, location does not impact vectors at all. All right. By the way, I want to talk about notation for vectors. So typically, kind of like how X was our normal name for a variable with just numbers, V is going to be kind of our default letter for vectors. Now, the way I'm going to write it to be consistent with Dr. Huang, I think this is the way she writes it, is you just kind of draw an arrow over the symbol here. So this is one way of writing it. Another way you might see is something kind of like this, where it's kind of like you're drawing an arrow, but then you got lazy. So it's almost like kind of like an angle symbol here. This is also something you might see a fair bit. One kind of uncommon notation, but does show up somewhere, is to draw the symbol and then put a little tilde underneath it. This also is a symbol for vectors. I don't think you see this one too often, but some people, I actually kind of like this one, honestly. I feel like it's easier to draw because it's one stroke. But yeah, this is another notation you might see. But all of these mean the same thing. All of these are vectors. All right, let's see. So in addition to adding vectors together, we can also multiply vectors by what are called scalars. And what's a scalar? A scalar is just an ordinary number. So that's kind of a fancy name for that. Why is it called scalar? Well, effectively what a scalar does is it scales the size of the vector. So for example, if I take, say, c equals 2, and I multiply it by my vector u, then we end up with a vector pointing in the same way, but it's going to be twice as long. So this is going to be 2u. It's pointing in the same direction, but is twice as long here. All right, and then what about a different c value? C equals -1/2. If you ever have a negative scalar value, what does that do? It points it in the opposite direction. This might be kind of familiar from polar coordinates. You guys at least very vaguely remember those from Calc 2. When you have a negative, it goes the other way. So rather than pointing in this direction, we're going to point in this direction. But since it's -1/2, we're only going to be half the length of this. So that's c is -1/2. What if c is 0? In that case, we kind of just have like a little dot right here, and this is called the 0 vector. So it's kind of hard to distinguish a 0 vector from a point here. So the way we write that is 0, and then we put a little vector symbol over it. I think it's pretty clear from these pictures right here. If you multiply a number by a vector, it's either going to point the same way or in the opposite way, but either way, you're going to be parallel. So if you multiply a vector by a scalar, then it's going to be parallel here. What is the difference between a vector of 0 magnitude and a point? I'm going to get to the difference between points and vectors in general in a little bit, and that will include the 0 vector. So I'll get to that in a little bit. Does the 0 vector lose its letter? One way to think of this is if we have 0 times u, then 0 times u will be the 0 vector, and then we write it like this. This is technically what's going on here. All right, great. So let's move on to the next page here. Let's see. So let's try a practice problem with this. So Alberta pushes on a post in the direction southeast to 30 degrees, so that's this way, with a force of 60 pounds. So that's the size of this force going this way, and the arrows are drawn proportionally how big this is. And then Albert pushes on the same post in the direction 60 degrees southwest with a force of 80 pounds. So this is going to be a length of 80. What are the magnitude and direction of the resulting force? So the way we're going to do that, well, actually one basic physics fact we need to have, if this is F1, and and this is F2, like the second force, then the total force, which I guess I'm just going to call F, is F1 plus F2. So if more than one force is working on something, you just add them together to see what the total amount of force is. All right, so effectively we just need to add these vectors together, and we just learned two different ways of doing this. I'm going to use the tip to tail method. I'm personally more comfortable with that, but you could also do this problem by using the parallelogram method. So what I'm going to do is I'm going to start off with this vector right here, and then I'm going to make a copy of this one at the end of it. So it's going to look something maybe like this, and this is 60. And then my resulting vector is going to go from the start of the first one to the end of the second. So this is going to be my capital F. And this is the force that I want. Now we need to know what its magnitude is, and we also need to know what its direction is. So we should probably give some kind of angle here. All right, now one interesting thing to note here, let me ask both the in-person people and the online people, what is the angle between these two vectors? What's the angle here? Yeah, 90 degrees, right? Because it's 60 degrees here and then 30 degrees right here. So in total, it's 90. That means that this is a right angle right here. So I'm going to put the little box. Okay, now let's think about this. I'm going to draw a copy of this triangle. Okay, so if we have something with 80 here, and we have our right angle, and then we have 60, what number goes into both 60 and 80? What's the greatest common factor of those two? Does anyone know? Looks like the chat is saying 20. So 20 is the biggest number that goes into both of these. So technically this is 4 times 20 and 3 times 20 here, right? So if this side effectively has a length of 3 20s and this side has a length of 4 20s, then what is this going to have? That's right. This is technically a 3, 4, 5 triangle, only it's scaled bigger. So it's going to be 5 times 20 or 100. So we know already that the magnitude of this force, since this is a 3, 4, 5 triangle, is going to be 100 pounds. But what we need to figure out now is the direction in which this force is being applied. And it seems like they're indicating direction by these degrees right here. Okay, so let's see here. What I'm going to do is I'm going to try to figure out what this angle is. So the angle inside this triangle, I'm going to call it theta. Now notice that theta isn't our answer. Theta is not the answer here. We really want this one right here. But since the whole thing is 60 degrees, if we figure out what theta is, then this will be 60 degrees minus theta. And that's going to be our angle here. But first we need to figure out what theta is going to be. All right, now let's see. So if we want to know what theta is, I don't think 3/4. Sorry, where we're going to figure out what theta is by using a tangent. So tangent of theta, tangent is what over what in terms of adjacent, hypotenuse, opposite? Yeah, opposite over adjacent. And the chat is kind of saying a lot of different things. Y over X, opposite over adjacent, 60 over 80. So this is opposite over adjacent. And then, so that means that our opposite side, the opposite to this angle is 60, and our adjacent side is 80. So tangent of theta is going to be 3/4. But what I was trying to say earlier is that 3/4 is not a common value for tangent to obtain. There's not like a pi over something you could plug into tangent to get that. So we're just going to have to settle with theta is arctan of 3/4. Okay, so that's what theta is. And then in order to get our direction, all we do is we just do 60 degrees minus arctan of 3/4. Now watch out, if you do arctan of 3/4 on most calculators, this will spit it out in terms of radians. So we would need to convert this angle into degrees. So I'm going to put the little degree symbol there. And if you go on your calculator and you actually do that, what was the answer here? I think I wrote it down. It's about 23.13 degrees. So that's how far you have to tilt away this way to have the direction of our force here. All right, so since we got both a magnitude and a direction, that means we found our vector here. All right, wonderful. So that was a good example starting off here. Let's see here. Direction is relative to the post, says the chat. Yeah, that's right, because they measured these directions of these vectors relative to the post as well. All right. So that's kind of our geometric interpretation of a vector here. Oh, actually, there's a few other questions in the chat I want to talk about. Could you also have slid the 80-pound line down to meet the arrowhead of the 60-pound line? Yeah, so we could have done tip to tail back here, starting with this one and then drawing the 80 down there. And you would see that it would create the same vector. So the problem would have been pretty similar if you would have done it that way. Any of the ways you could have added this up would have resulted in the same answer. All right, let's see here. So let's move on to this real quick. All right, sorry. Unfortunately, I don't have time to answer all the questions. If there's any at the end of class, I'll try to answer them then. All right, now what we're going to do now is we're going to talk about vectors algebraically. So first we were looking at them geometrically, kind of just moving things around. But now we're going to talk about them in terms of their components. The most common way of doing this is expressing things as a position vector. So a position vector u, which has components u1, u2, and u3, and this is the x component, the y component, and the z component here. What was I saying here? Yeah, the position vector tells you how to get from the origin all the way to whatever this point is right here. So if I were to follow from the origin out with this u vector, I would arrive at this point, u1, u2, u3. So effectively, a vector is telling you the directions to get from the origin to a specific point. Now, the thing about vectors is that, remember, they're the same even if you move them to a different location. So if I drew the same vector right here, notice it has the same magnitude and direction. This is also going to be u. Even though it's not starting at the origin, it's still going to be u right here. And this is kind of where things get a little bit tricky, because we kind of, later on in the class, we're going to kind of treat vectors and points as pretty similar, or at least points and position vectors. It's easy to get them mixed up. The way to keep them straight is I like to think of vectors as like a conveyor belt at an airport. So I'm pretty sure most people have been to an airport, right? So in order to get from between terminals quickly, you sometimes walk on those like conveyor belts that kind of scoot you along a little bit faster. The vector is effectively a conveyor belt that takes you from the origin all the way to this point. But then let's say you move the conveyor belt to a different part of the airport, like you moved it over here, it's still going to move you in the same way, but it's not going to have you end up at the same place. So vector is like a conveyor belt, but a point is a location specifically. So if I moved, for example, this point to here, that would be a totally different point. Whereas if I move this vector to here, it's the same vector. So that's kind of one thing I want to emphasize here. It's easy to get them mixed up. And it's also, the notation is very similar too. We kind of have these angled brackets for a vector and then just curved parentheses for point. All righty. So let's see here. So for example, in this case, if we have P1 to P2, we reach P2 from P1 by our U vector here, then the components of that will be X2 minus X1, Y2 minus Y1. Oh, thank you, sorry about that. And then we have Z2 minus Z1. So if you want to get from this point to here, you have to move this much in the X direction, this much in the Y direction, this much in the Z direction. And so these are equal to our components U1, U2, and U3 right here. All right, now let's say we want to express the length or the magnitude of our vector here. All right, so the length of this vector is actually just the distance from this point to this point right here. And last time we actually came up with a formula for that. So we're going to use the distance formula to get ourselves an equation for the size of a vector. So the distance between this point and this point is square root of x2 minus x1 squared plus y2 minus y1 squared and z2 minus z1 squared. But since another name for each of these is just u1, u2, and u3, we're going to have u1 squared, u2 squared, and u3 squared. So if you ever want to figure out how big a vector is or how long it is, you simply square each of the components, add them together, and take the square root. That's how we're going to find the magnitude or the length of a vector. All right. So we can also find expressions for the sum of two vectors and a scalar multiple of two vectors using these components. And I think that, like most of you guys have seen vectors before, this is going to happen in the obvious way. So if we're adding u and v together here, I have u1 plus v1. That's going to be my first component. And I add the two middle components. And then I add the two last components. So thankfully, adding two vectors together is pretty easy. You just add all of the matching components together. Scalar multiplication is also pretty easy. If I have c times u1, u2, u3, then I'm just going to multiply each one of them individually by c. So I have cu1, cu2, cu3. All right, there we go. So it's not too, it's kind of pretty easy to do these things once you have this algebraic or component form for vectors. All right, let's scooch up a little bit. All right, so let's take a look at an example here. All right, so if u is this vector, 1, negative 1, 2, and v is this vector, then we're supposed to find 2u minus v, and then we find out how long it is. All right, well, let's see, 2u minus v, that's 2 times 1, negative 1, 2, minus 0, 1, negative 1. All right, well, let's do 2 times this. That means we just multiply all of the numbers in here by 2. So 2, negative 2, and 4. 0, 1, negative 1 right here. All right, and then I'm going to subtract. So I do 2 minus 0, that's 2. I do negative 2 minus 1 is negative 3. And finally, I do 4 minus negative 1, giving me 5. So this right here, this is going to be 2u minus v right here. All right, and then now I want to find the magnitude of this vector. Well, we just figured out a formula for doing so. The magnitude of 2u minus v is where we have the square root, and then we square each of these components here. So we have 2 squared, negative 3 squared, and 5 squared. All right, let's see, that's 4 plus 9 plus 25. So we end up with the square root of 38 as the magnitude for this vector here. It looks like Osaji online has a question. What's your question?
Oh, sorry. Yeah, you were talking about the distinction
Oh,
between.
I don't think the volume's on here.
Hello?
I don't think he can hear you right now.
Ah, damn, that sucks.
It seems to be on the computer here. Can you type it in the chat maybe? For some reason, it's not playing here.
All right.
Goose go. Goose go.
Yeah, I'm sorry, guys. This is kind of a mess.
Goose go.
Okay, what? All right, you guys, please don't make a bunch of noise in the chat just because we can't hear it. Yeah, once they figured out I couldn't hear them, they started like going nuts. Okay, yeah, so just please let Osaji ask his question here. We want to make sure we have time to finish. All right, I'm really sorry, guys. I have to move on here and make sure I finish this in time. So feel free to ask me after class, though. All right. Let's see here. So once we okay, so once we figure out how to work with these vectors algebraically, then there end up being a bunch of properties right here. So a lot of these properties are more or less kind of self-explanatory. Like if you add a vector this way and then you add it the other way, it's going to add up to be the same thing. You add two vectors together to add a third one, that's the same as if you added the last two and then added the first one. If you add zero vector, it's not going to do anything. If you subtract a vector from itself, it's going to give you zero. And a lot of these other properties are kind of similarly pretty obvious, I think. Now, one thing you'll notice that isn't here is they're not saying anything about, so there's nothing said about multiplying two vectors together. So for example, like we have a scalar times a vector right here, but it doesn't say anything at all like, oh, what if I want to do u times v? Like, what does that mean, or what properties does that have? And it turns out there's going to be multiple interpretations of multiplying vectors together, but that's going to be for a future lesson. But for now, we can only add vectors together and then multiply by a scalar. All right, so I'm not going to bother with these properties. All of them are already on the notes here. Okay, another piece of a terminology here is the unit vector. And a unit vector simply just has length 1. It could be in any direction you want, so long as your length is going to be 1. Now, a formula for getting a unit vector is this. Now, let's say I want to get a unit vector in the direction of u. The way I express that is going to be u, and then I put this little kind of angled thing over it right here. And this is pronounced u hat because it kind of just looks like a silly little hat or something like that. And the way we get this is we take our original vector u and we divide it by its magnitude. So effectively, we're scaling the size of our vector down to 1, and then all we have left is the information about its orientation or position. Yeah, chat's saying it looks like a witch hat. Yeah, it kind of does. All right, now if u is a unit vector, then the absolute value of c times u, what's that going to be? Well, that's going to be absolute value of c times the magnitude of u hat. But remember, since u hat is a unit vector, what number is this going to be right here? 1, that's right. Yeah, by definition, this has a magnitude of 1. So then we end up just getting absolute value of c out of this. So if you ever multiply a scalar by a unit vector, it's just going to be the absolute value of that number right there. And notice the magnitude is always positive. Since it's defined by a square root, it's always going to be, or I guess, greater than or equal to 0. You're never going to have a negative magnitude for a vector. All right, so here's an example about unit vectors. Find the unit vector in the direction of this one, -1 to -2. All right, well, the name we have for that is w hat, and that's going to be the w vector divided by the magnitude of w vector. Now, I want you guys to be very careful with this because it's easy to mix up this notation. But sometimes you'll see people denote the magnitude of a vector as just the symbol for the vector without the arrow above here. Now, this is why it's especially important that you put arrows on all of your vectors so you won't mix it up with the magnitude of it, because this is a very common notation to just write the letter without the vector to mean the magnitude here. So when you are writing the vector, like in this case, you need to put the arrow every single time right here. Can I go back for a second? Yeah, I can go back up here. All right, anyways. So our vector in this case was -1 to -2. And then let's do our magnitude down here. So the magnitude of w is -1 squared and 2 squared and -2 squared and a square root. All right, well, let's see. What's this number going to be down here? 1 plus 4 plus 4. This is the square root of 9, aka 3. So effectively what I'm doing is I'm going to divide every single component here by 3. So I have negative 1/3, 2/3, and negative 2/3. And this right here is going to be the unit vector in the direction of W. And you could check for yourself here. If you take the magnitude of this, you will end up getting 1 for that. So that's a good way to check your work if you're finding a unit vector. Okay, this question's a little bit more involved here. Find the vector that has the same direction as this, but has length 3. So how are we going to approach this problem? What we're going to do is we're going to find a unit vector in this direction, and then what do you think we're going to do with that unit vector? Multiply it by 3. That's right. Both the in-person and the chat people got it. So first, let's find the unit vector for this. I guess this doesn't have a name, so I'm going to call it V. So V hat is V over the magnitude of V. All right, so this is going to be -2, 3, -6. And let's see, what's the magnitude of V here? That's going to be -2 squared plus 3 squared plus -6 squared. Okay, what's this number going to be? Let's see, we have 4, 9, 36. All of those make 49. And then the square root of 49 will give us 7. Okay, so that means I'm going to divide all of these components by 7 here. So I have -2 over 7, 3 over 7, and then -6 over 7. Remember, this isn't our final answer here. This is simply the unit vector in this direction. But this has a length of 1. So what we really want is we want 3v hat, which is going to end up being -6 over 7, 9 over 7, and -18 over 7. All right, so there we go. So that was kind of a twist on the previous problem here. All right, let's keep going here. Let's see. Okay, so that's unit vectors and finding vectors in certain directions. Now, another way you may see vectors expressed is in this IJK notation. So these are called the standard basis vectors. And so I is the unit vector pointing in the direction of the x-axis. So if I put my 3-dimensional coordinate axes here, then I hat is a vector pointing 1 unit in the x direction. This is I hat. And it's often written as I, but then rather than a dot, it just has the hat instead of the dot. And then in the same way, j is the unit vector in the y direction. It's written in the same way as I hat, where you just replace the dot with the hat. And then k hat is the unit vector in this direction. And k has no dot, so you just put an extra hat on it. All right, now, because of this, what you can do is you can write any position vector you want in terms of this I, j, and k, at least in 3-dimensional space here. So say, for example, I want to express the point A, B, C, then I would write that as A times I hat plus B times J hat, and then plus C times K hat. So this will be another very common notation for vectors. You may see them written in component form like this, and then you might see them written in terms of the basis vectors here. Will I with a dot and a hat also be appropriate? Yeah, no one's going to take points off if you do like this or something. That's totally fine too. All right, so let's try to use this new notation here and get comfortable with it. All right, so if the velocity vector v is 3 times I minus 4 times k, and it's a velocity vector, express v as a product of its speed times its direction. All right, so one fact about velocity is it's going to be speed, which is a scalar, by the way, and then it's just going to go times a unit vector. So this kind of points in the right direction of the velocity, and this is going to say how fast we are going in that direction. So this is just another way of saying a scalar times the unit vector. Kind of like back here, we can imagine almost like 3 is the speed and then v is the direction in which we're moving. Okay, so let's figure out both of these components here. All right, so let's see here. So the magnitude of our vector is going to be the square root of 3 squared. It doesn't look like we have a j at all. And whenever we don't have one of these letters, we just assume that it's 0. So we're not going to have any kind of y squared in here, but we will have negative 4 squared. And then our vector here is 3i minus 4k. Or sorry, this is v hat. We'll get to that in a moment. Okay, so then what's this number going to be right here? That's right. Yeah, it's going to be 5. And this is another 3, 4, 5 triangle example. So if we do 5 times v hat, that's going to give us our v right here. So this is going to be our speed. And then we need to know what direction we're moving in. But remember, the direction is simply the original vector divided by the magnitude right here. So in this case, we're going to have 5. And then our original vector divided by 5, the magnitude, will be 3/5 I hat minus 4/5 k hat. Because we got the 3 and the negative 4 from this. And then we got the 5 from down here, which we already figured out. So there, we have it times the speed. We have the speed times the direction here. All right, and that's actually kind of just expressed in the next one here. You could express any vector as its magnitude times a unit vector, which indicates its direction. So that's kind of the summary of what we just did with the specific example. All right, coming down the home stretch here, how much time do we have left? Let's see here. Oh, good. Looks like we're actually good on time here. All right. So let's see here. Will those ever cancel out? Yeah, at any time you could just cross these out and just get u. It's easy to see why this is true. But a lot of times we want to know what the unit vector is and what the magnitude are separately. So this is kind of a way in which you could do that. All right. So this is going to be a physics problem, and spoiler alert, we're going to see a fair amount of physics problems because physics is probably one of the fields that applies math the most. So a lot of our practical examples are going to come from that. All right, anyways, so 100 Newton weight is suspended by 2 wires as shown below. So we have F2 and F1. Find the forces F1 and F2 acting in both wires. All right, now, when we say find these forces, we're finding vectors, right? So it's not enough to just find out how strong these forces are. We also need to know in which direction they're going. So we need both magnitude and we need direction. So it's not enough to say like, oh, this is 50 newtons or something. We need to know 50 newtons in which way. Okay, so let's see here. So presumably this thing, I guess it doesn't say it in the problem. Well, it says suspended. I guess that's good enough. We're assuming that this isn't moving at all. This is not accelerating. And that means everything is in what's called equilibrium. Everything's just kind of resting at peace. It's not going to move unless it's disturbed. So we have, on the one hand, this 100 Newton weight going down like this. So in order to balance that, the vertical components of F2 and F1 need to end up equaling 100. So what I'm going to do here is I'm going to split F2 and F1 into 2 pieces. So note here that this is going to be 60 degrees as well by geometry. We have this angle right here. It's going to be the same as this one. Now the vertical component of this force right here, F2, Actually, let's do the horizontal component since that's come first with the notation. So if I want to get the horizontal component right here, that's going to be the magnitude of F2. So remember that we just write the letter when we want to do the magnitude here. And then what do you think I'm going to multiply this F2 by to get its component in the horizontal or x direction? What function do we often associate with x? Cosine, right? So we're going to multiply by cosine of 60 degrees. And that's going to give us how strong F2 is in the x direction. So this is F2 cosine of 60. And then similarly, if we want to find the vertical component of F2, it's going to be F2 sine of 60. All right, and then I bet you could guess what's going to happen with F1. If we kind of draw this extra line right here, we see that since this angle and this angle need to be the same, this is going to be 30 degrees right here. All right, and so that means that F1 is going to be F1 times cosine of 30 degrees. But actually, since this angle is kind of opening up in the wrong way, usually angles open up like this, but this is opening up on the wrong end of the x-axis, that's actually going to have a negative right here. All right, and then the vertical component will be F1 sine of 30 degrees. I see some requests in the chat to kind of explain where this comes from right here. One way to see where this comes from is, let's say we wanted to know the magnitude of F2, right? So technically we have to do this squared, and then we add in this squared right here. All right. Now, both of these have F2 squared in common. So what I could do is I could factor out that F2 squared, and then I have cosine squared of 60 degrees and sine squared of 60 degrees. And I think we all know what's coming out next. This is going to end up being 1. So then we end up with our absolute value of F2. So this is why this works. Another way to see this works is you can kind of draw a unit circle with radius equal to F2. That's another way of seeing that this is true. But in general, whenever you want a horizontal component of something, multiply by cosine of whatever angle it is. And if you want a vertical component, multiply by sine. That's going to be true in general. All right, anyways, back to our problem here. Now we know the different components of our forces here. All right, so we are going to have two equations. The first equation we're going to have comes from the fact that the vertical components of F1 and F2 need to balance out the 100 newtons going down this way, because it's not moving. We can't have a net force, so it needs to be equal. So if I add the vertical components together, I have F1 sine of 30 and F2 sine of 60. Whatever that is, it needs to equal 100. So it's going to balance out. Oh, sorry about the paper. All right, so this is one equation that we have. And then the other equation, actually, let me see if you guys can figure this out. So it's not moving horizontally at all, right? But the only forces horizontally are the horizontal component of F1 and the horizontal component of F2. So can anyone see what the equation for the second equation we're going to write down is? Has to do with the horizontal components. Yeah. That's absolutely right. This is what our audience member said. Since there's no force at all going in the horizontal direction, then this is going to be our equation here. But another way of writing this is we could say that F1 cosine of 30 needs to equal F2 cosine of 60 right here. All right. So anyways, with this information, this is actually enough information for us to find out what F1 and F2 have to be. All right, so let's see. So cosine of 30 degrees, that's going to be √3/2. And then cosine of 60 degrees, that's going to be 1/2. So what I could do is I can multiply both sides of this by 2. And so I see that √3F1 is the same as F2. So what I'm going to do, since I use this equation now, I'm going to take this information and put it into my other equation right here. So when I do that, I get that F1 sine of 30 plus √3F1 sine of 60 is 100. And where did I get this from? Remember, I can replace this F2 right here with √3 times F1, because that's what we just found out. And thankfully, this equation now only has one variable right here. All right, so let's see. Sine of 30 degrees. Sine of 30 degrees is going to be 1/2. And we have √3 F1, and sine of 60 is √3/2. Okay, I'm going to multiply everything by 2 to get rid of these fractions. So I have F1 plus, let's see, so this 2 will go away, and then √3 times √3 is 3. Then I now have 200. So I multiply both sides by 2 right here. And then finally, last I checked, 1 plus 3 is equal to 4. We have 4F1 is 200. And that means that the magnitude of F1 is going to be 50. And I think our unit was newtons right here. All right, and then using this piece of information, we can easily get what the magnitude of F2 is going to be. F2 is going to be the square root of 3 times 50 newtons. Okay. Oh, I see a question in the chat. Did you forget the negative? Yeah, so the negative appears right here, and then I added it over to the other side, and it became positive. That's what happened. Now, am I done here? I know how many newtons this is. Am I finished with this, or is there something else I need to do? What do I need to do now? Yeah. It's okay. Yeah, we just need, the chat is saying this, we need to specify a direction as well. These are the magnitudes of F1 and F2, but we need to know what direction they're going in. Now, one way we could do that is we could just write them in component form. So we have F1. Remember, way back when, F1 is the magnitude and then times this stuff right here. So we could say that F1, let's see, we have negative F1 times cosine of 30, so it's negative 50 cosine of 30. And then F1's vertical component is 50 sine of 30 degrees right here. Okay, and then if I evaluate this, cosine of 30 is going to be √3/2. So it's negative √3 times 25. And then sine of 30 degrees is 1/2, so we have 25. And since now I'm writing this in vector form, and I have that the vector equals something, this specifies both magnitude and direction. I can find the magnitude of this using the formula, and the direction I can find by solving for the unit vector. And we could do the same thing with F2, of course. So F2, we go back up here and see what F2 was. It's the magnitude times cosine of 60 and the magnitude times sine of 60. All right, so F2's magnitude was √3 times 50. And then we have cosine of 60 here. And then we have √3 times 50 times sine of 60 degrees here. All right, and then when we do the arithmetic for this, let's see, this is going to be 1/2. So we get √3 times 25. And then this is going to be √3/2. So let's see. This is √3/2. We divide 50 by 2, and we get 25. And then we do √3 times √3, we get 3. AKA, this is going to end up being 75. And that's what our F2 is. And one way we could check our work, we could see that we did this right because the horizontal forces are equal and opposite. They totally balance each other out just like we wanted them to. And if we add the vertical forces together, remember F1 and F2 were working together to lift this 100 Newton weight. And if we add together these two forces, lo and behold, we get 100 units. So with any physical problem, and this goes for your physics classes too, make sure that your answer makes sense. Like if we didn't get these to add up to 100, that means we kind of did something wrong because that was the whole point of these vertical components. All right. So anyways, that was a problem where we we're using vectors here. All right. What are we doing on time? Oh, perfect. It's just about over here. Yeah, I'm really sorry, guys, especially for those in the chat. I couldn't hear you guys. I'll try to work on that for next time. But thanks everyone for being a good sport about this. And yeah, I guess I'll see you guys on Friday where we'll continue learning about vectors here.
Professor Manley?
Okay. Yeah, and people, I can't hear you, but feel free to ask questions in the chat. I can answer those for maybe a few minutes. And people in the live section, if you want to ask questions, you can feel free to come down here. Oh, let me stop the recording.